Today we're going to learn about on compressor. For handling gas volume at pressure rises, then fan can accommodate several distinct type of equipment are used. For example, a turbo blower or centrifugal compressor is widely used to move large volume of gas for pressure rises from about 5 kilopascal to several thousand kilopascal. The principle of operation for a turbo blower are the same as centrifugal pump, as you can see from the figure. The turbo blower resembles a centrifugal pump in appearance, and the main difference being that the gas in the blower is compressible. In the fan, the gas is assumed to be incompressible, but for blower it is a compressible gas. Equation for isothermal compression. So we have two types of compression, isothermal and adiabatic compression. For isothermal compression is the reduction in the volume of gas with no changes in temperature. Where the gas is cool as it is compressed, P over rho is a constant equal to RT over M. R equal to 8314 joule per kilogram in SI unit and 1545 feet per pound force per pound mole in degree Rankine in English unit. The work for isothermal compression as shown below, and T1 equal to 2 since the process is isothermal. So minus Ws is mechanical energy in joule per kilogram. P1 over rho 1 integral dp over p. So the final equation is 2.3026 RT 1 over m log P2 over P1. For the diabatic compression of the A is defined as the compression in which no heat is added or subtracted from the A, and the internal energy of the A is increased, which is equal to the external work done on the A. The pressure of the A is more than the volume as the temperature increases during compression. For diabatic compression, the fluid follows an isentropic path where gamma equal to Cp over Cv. The ratio of capacity is followed. Ws mechanical energy equal to gamma over gamma minus 1 RT 1 over m. So P2 P1 then minus 1 here. The relative temperature related by T2 over T1 equal to P2 over P1 gamma minus 1 over gamma y. To calculate the brake power when the efficiency is this, where m equal to kg gas over second and w as mechanical energy is joule per kilogram. So this is a equation minus WSM over efficiency times 1000. So for the adiabatic compression, the gamma value is approximately 1.4 for A and 131 for methane and so on is given normally. Example, the single stage compressor is used to compress 7.56 times 10 to the power of negative 3 kilogram per mole of methane gas at 26.7 degrees C from 137.9 kilopascal absolute pressure to 551.6 kilopascal absolute pressure. Calculate the power required if the mechanical efficiency is 80% and the compression is adiabatic. So for part 1, P1 here is 137 kPa, P2 is 551, 552 kPa. Molecular weight of methane is 16 kilogram mass over kilogram mole, and T1 273.2 plus 36.7. So you get almost 300 Kelvin. The mass flow rate per second is 7.56 kilogram per mole times weight molecular weight of methane. You get what, 0.121 kilogram per second. So this is methane, so the gamma is 1.31, and P2 over P1 is 4. I think 4. Yeah. Using a thermal compression equation, this equation, previous slide 22. So the mechanical energy, yeah, the gamma is 1.31 given. 1.31 minus 1, R is 8314, T in Kelvin 299.9. This M is molecular weight of methane 4 over 1, which is this P2 over P1. And you should get to 56300 256,300 joule per kilogram. Using a brake horsepower equation, this is equation, so we get like 38.74 kilowatt for isothermal compression equation. Repeat part A, but for the case of isothermal compression, for this is adiabatic compression. So for isothermal compression, we use this equation. Mechanical energy equal to 2.3026 RT1 over M log P2 over P1 is exactly the same for the value here. Get like slightly lower, 216,000 joule per kilogram compared to here, 256. So the brake kilowatt is 32.67 kilowatt or 43.8 HP. And isothermal compression uses 15.8% less power. Uh, the metering of fluid. It is important to be able to measure and control the number of material entering and leaving a chemical or other processing plant. Since many of these material are in the form of fluid, they are flowing in pipe or conduit. Devices that are widely used for fluid metering are the pitot tube, venturi meter, orifice meter, and open channel weigh. So for pitot tube, this is how it's looked. Figure 5.3-1. A is simple tube. B is tube with static pressure hole. The pitot tube is used to measure the local velocity at a given point in the flow stream and not the average velocity in the pipe, as you can see here. Measure in the middle. In figure 5.3-1A, a sketch of this simple device is shown. One tube, the impact tube, has its opening normal to the direction of flow, while the static tube has its opening parallel to the direction of flow. This is the impact tube, static tube. The fluid flow into the opening of at point 2. The pressure builds up and then remains stationary at this point called the stagnation point. The difference in the stagnation pressure at point 2 and the static pressure measured by the static tube represent the pressure rise associated with the deceleration of the fluid, the delta H. The manometer measures the small pressure rise. Equation in the tube. Velocity in the duct is V equal to Cp to P2 minus V1 over rho, where V is the velocity V1 in the tube at point 1. P2 is the stagnation pressure, rho is the density of the flowing fluid at the static pressure P1. In CP is a dimensional coefficient that varies between 0.98 and 1. The value of the pressure drop P2 minus 1 or delta P and PA is related to DH, the reading on the manometer as follows. So delta P is equal to delta H rho A minus rho times G, where rho A is the density of the fluid in the manometer in kilogram per meter cube and delta H is the manometer reading in meter. Exercise. A pitot tube similar to figure 5.3-1a is used to measure the airflow in the circular duct 600 millimeter in diameter. The pitot tube is placed at the center of the tube of the duct and reading that the H on the manometer is 10.7 mm of water. A static pressure measurement of 10 at the pitot tube tension is 205 millimeter of water above atmospheric. The pitot tube coefficient Cp equal to 0.98. Calculate the velocity at the center and the average velocity. So part A, the properties of A at 65% PVC are mu equal to 2.03 times 10 to the power negative 5 Pascal PA Pascal second. This is the viscosity. Rho equal to 1.043. To calculate the absolute static pressure, the manometer reading delta H equal to 0.205 meter of water indicate the pressure above 1 atm. The water density as 1000 kg per meter cube and assuming 1.043 kg per meter cube as the A density. So here you get delta P equal to 0.205. This is the H. This one is rho A minus rho G. Rho A is the water density minus A times gravity G, get like 2008 Pascal. Then the absolute static pressure P1 equal to 1.1 times to the power of 5 plus 0.02008 times 10 to the power of 5 equal to 1.033 times 10 to the power of 5 Pascal. The correct air density in the flowing air is 1.063 kg per the cube. This correct value when used instead of 1.043 would have a negligible effect on the recalculation of P1. Calculate delta P for the pitot tube now. So delta P equal to delta H rho A minus rho G equal to 10.7 over 1000. So 10.7 you get from delta H here over 1000. So 1000 minus 1 is for water A and gravity. So you get like 104.8 Pascal. The maximum velocity at the center is V equal to 0.98 times square root 2 times 104.8 over 1.063. So 1.04 is coming from delta P, 1.063 is air. Where is it? Correct density of air. This is what is it? CP. So CP here is 0.98. So the maximum velocity at center is 13.76 meter per second. The Reynolds number using the maximum velocity is, when you calculate the Reynolds number here, so D is the diameter, 600 mm, 13.76 is the maximum velocity, 1.03 is the correct air density over mu, the viscosity. So you get like 4.323 times 10 to the power 5. So VAV over Vmax equal to 0.85, then VAV equal to 0.85 times 13.76, which is 11.7. So volume, so velocity average is 11.7 per second. VAV over Vmax. The ratio here is based on this equation. You see the Vmax rho over mu. You get like 10 to something, 4.3 here. It passes this line, so you get the VAV over Vmax equal to 0.85. A Peter tube similar to figure 5.31a is used to measure the air flow in a circular duct, 100 mm in diameter, which is exactly a similar question. But for this case, calculate the volumetric flow rate of the flowing air in the duct. So to calculate the flow rate, we have to calculate cross-sectional area of the duct. A equal to pi over 4 times 0.6, which is diameter of the pipe, times 2. So you get like 0.2827 meter square of sectional area. The flow rate is 0.2827 times volume average, velocity average 11.7. Calculate it before. So you get like 3.308 meter cube per second. Volumetric orifice meter. A typical sharp edge orifice is shown in figure 5.3-4 machine and drill plate having a hole of diameter d naught is mounted between two flange in a pipe of diameter d1. The pressure tap at point 1 is upstream, 2 is downstream. Measure P1 minus P2. The exact position of the two taps are somewhat arbitrary in one type of meter. The tap are installed with one pipe diameter upstream and 0.3 or 0.8 pipe diameter downstream. The fluid stream once past the orifice plate form a vena contracta of free flowing jet. Equation for orifice meter. The equation for the orifice is V naught equal to C naught over 1 minus D naught over D1 to the power 4 times square root of 2 P1 minus P2 over rho. Where V naught is the velocity in the orifice in meter per second. D naught is orifice diameter in meter, and C naught is the dimensionless orifice coefficient. So orifice here is this opening. The INRE is if the Reynolds number of the orifice is above 20,000 and D naught of D1 is less than 0.5. The value of C naught is supposedly constant and has a value of 0.61. Below 2000, the coefficient rises sharply and then drops. For measuring the compressible flow of gas in an orifice, a correction factor Y for A is used as follows, where M is flow rate in kilogram per second, rho 1 is upstream density in kilogram per meter cube, and A naught is the cross-sectional area of the orifice. For liquid, Y is equal to 1, the correction factor. So M equal to C naught A naught Y over 1 minus D naught over D1 to the power of 4 times square root of 2 P1 minus P2 rho 1. The permanent pressure loss depends on d naught over d1 in as follow, where beta equal to d naught over d1 and p4 is the fully recovered pressure for 8 meter downstream. For b equal to 1 over 2, the power loss is 75% of p1 minus p2. This is the equation. Example, a sharp edge orifice having a diameter of 0.056 cm is installed in a 0.151 meter pipe through which oil having a density of 0.87 kg per meter cube and a viscosity of 4.1 cp. Exploring. The measure pressure difference across the orifice is 93.2 kilonewton over meter square. Calculate the volumetric flow rate in meter cube per second. Assume that C naught equal to 0.61. The solution P1 minus P2 is delta P is 93.2 kilonewton per meter square, or this D1 equal to 0.1541, D naught is 0.0566, the orifice. D naught over D1 is 0.368. The volumetric flow rate V naught pi D naught square over 4. So V naught here, oh sorry. So V naught equal to, calculate the V naught first. V naught equal to the equation given, equation for orifice. So 0.61 is from the C naught here. 1 minus 0.36, okay. D naught over D1. 2, this is the delta P over 978 is the density. So you get V naught equal to 8.97 meter per second. Then you can calculate the volumetric flow rate equal to V naught pi D naught square over 4. And then you get 0.02257 meter cube per second. And calculate the Reynolds number. Which is, so D naught is 0.05566. 8.97 is V naught here. Rho is 878 over viscosity 4.1 Cp equal to, this is center poise, so equal to 1.087 times 10 to the power 5, and the Reynolds number is above 20,000. If it's below 20,000, the coefficient of C naught is not equal to 0.1 here. Thank you.